Okay, so today's topic is conversion of context-free grammar into an equivalent push-down automata. So we have seen the lectures on the other slide, which is provided by the uh, author of the book. So let's have a quick way to convert a context-free grammar into a push-down automata, and we need to have the following steps to follow. So the very first thing which we need to establish is to have the tuple of context-free grammar. So we have to write down the whole set of tuple of context-free grammar. So very first step is to convert the given production of any context-free grammar into GNF. This will definitely help us to establish an easy way to convert a context-free into push down automata. And you guys all know that what is GNF? GNF is the Greback normal form, which defines that every production should start with a terminal or can have many non-terminals, but followed but there must be a terminal in the beginning. So step number 2, the PDA will only have one state, that is Q. Step 3, the initial symbol of the CFG will be the initial symbol of the push down automata. So the start symbol for both the grammar and the push down automata remains same. Step number 4, which is the most important step, is the identification of non-terminals and the non-terminal symbols. We need to follow the rule of converting the transition function in a way that the production reduces into its every non-terminal should be reduced into its production, you can say. So here we can say that here is the initial state which shall remain same, as we have mentioned over this, that the PDA will only have one state, and we don't need to see the input string. So here is the non-terminal that is supposed to be on the stack top. So this stack top variable is producing alpha. So if this is the production rule, so we can convert this production into an equivalent transition function. So if we are having all the transition functions for the PDA, we can easily construct the graphical representation of any push down automata. So whether we are having a graphical representation of push down automata or this mathematical representation, both are same, both are equivalent. Then step number 5, for each terminal. So we are actually having two standard activities, one for the non-terminals and the other one for the terminals. So for non-terminals, we need to have the transition function which translates the production rule. So that is the implementation of production rule. In step number 5, what we are doing, we are simply popping out the terminals. So how we can pop out the terminal? The transition function defines with a state, that is Q. We are reading A as an input sequence, and at the same time we are looking A on the stack top. So if this is the case, which is basically for the terminal symbol, so what we need to do, we need to have the state and epsilon. So epsilon means that we are popping out the terminal from the stack. So we have to create all the transition functions for each and every terminal symbol. So this is the basic idea of converting any CFG into PDA. So let's have a quick look with the example. So here's the example. We are having a CFG where S produces 0 S1 as well as S produces A produces 1 A0, S and epsilon. So context-free grammar must be simplified by eliminating the unit productions, and we need to convert into GNF. So we quickly resolve this grammar into Grayback normal form. So the Grayback normal form says that every production starts with the terminal and can have lots of non-terminals after that. So terminal, lots of non-terminals. It can also produce epsilon. So if any grammar accepts epsilon, so here the grammar S accepts A and A accepts epsilon. So that means that S is also accepting epsilon. So if the start symbol is accepting epsilon, then we already knew that in any of the normal form this production is acceptable. So here S is producing epsilon, fine. Then any of the non-terminal is producing terminal is fine for the GNF. So here is the GNF conversion of the given CFG. So let's see how we can convert. So first of all, how many terminals and non-terminals do we have? We are having 1, 2, 3 product non-terminals, and every non-terminal contains different productions. So for every non-terminals we need to translate these productions into the transition function, and then we are having two terminals. For these terminals we need to write the popping out productions. So let's see, for S what do we have? For S is producing 0 as X, so this comes up with epsilon. Then there is a set, so we are having OR symbol in between. S is also producing 1 SY, or S is producing epsilon. In every transition you can see that the state remains same, state is not changing. Then there is another transition function for the next non-terminal, that is X. So X is producing 1, so here we can write X is producing 1. The third one is Y is producing 0, so Y is producing 0. So these productions are translated into transition functions in this group. The next group R4 and R5 belongs to the terminals. These are the popping out terminals. So Q is the state, 0 is the input symbol, and 0 on the stack top. So we are simply taking this 0 from stack and producing and placing epsilon over there. So we can also say that Q is if this is the Q, so we can say, if we are saying that this is Q naught in all of these states, so we can say that Q naught is being moved towards Q1. It happens only whenever we are dealing with any terminal. So whenever we are talking about the terminal, we can switch over the state. For the next, we can say Q1 and we are moving towards Q2. So this is how we can define the production rules into the transition function, as well as we can create the popping out scheme for every terminal. So these are the popping out transitions. Popping out ones. So there is another example in which we have already used a context-free grammar, which is already in Grayback normal form, so we don't need to convert this CFG into GNF. So here is the tuple for A states. These are the input symbols on the stack. Transition function, starting state, and S is your set of final state. Sorry, Q is the final state and S the start state, and we are having Q that defines the endpoint. So we are having different things over here. So let's see how we can deal with it. So 1, 2, 3, 4. 4 productions do we have, and let's see how we can design these 4 productions. But there are only 2 non-terminals, that is S and B. So 1 for S and 3 for B. So S is producing 0BB, fine. B is producing 0S, B is producing 1S, and B is producing 0. So we can write all the production transition functions in one set or separately. It's up to us. for zeros and ones, for example, this is Q0, so we can jump to Q1 and popping out 0. From Q1 we can move towards Q2 and popping out 1. So these two rules help us to convert this context-free grammar into an equivalent PDA. So let's see how we can validate a string. So if this is the string which is 0, 1 and 4 zeros against the given PDA, so we need to validate this particular string with the help of the transition functions, which are basically PDA transition function. If this is the instantaneous description, that is the ID, and there is the another ID, so how we can move the value? The very first one is this is the input string, and your start symbol S, and S is converting into 0BB. The Q shall remain same, so we don't need to worry about the state. For every read, we are simply looking towards the transition function. So if this is the first movement, so we can see that okay, we are having a terminal on the top of the stack. So if we are having a terminal on this stack, so we need to implement the popping out of the terminal. So we popped out the terminal, so 0 and this 0 has been cancelled out with the help of a popping out scheme. Now we are having 1 on the top and B on the stack top. So how we can deal with this B? So we need to see that if we are having B, so we can have these three possibilities, either 0S or 1S or 0. So we need to choose 1 because we are having input 1, so this B is going to be replaced by 1S. Now 1 on the top, so we are popping out this 1, and now we are having 4 zeros and SB, so S can be translated into 0 SB, so with S is translated into 0 BB. Now on the top of the stack we are having 0, so again we are popping out 0 and cancelling these 0, so we are popping out the 0 over here. Now we are having 3 zeros and 3 B's. The B is going to be converted into 0 because of this particular 0. What we can do, we can have 0S as well, and there is another one which is 0. So for B we can have one of this production, and there is another production that is 0. So which one we can choose, it depends upon the input string. So we are choosing this one because we knew that all of these input values belongs to 1 zeros, and there is no 1 into it. So if there is 1, then we will jump towards S. So here we are cancelling out 0 by using the popping out production, and then we are replacing B with 0B, again popping out this 0, and now we are having 0 and simple B, and B is going to be reduced into 0, and finally we are having 0 in the input string as well as 0 on the stack top, so both can be cancelled with the help of popping, and in the last we are having epsilon. So we reach to the epsilon, that means we have eliminated the stack. So if the string is completed, the string is fully terminated, fully consumed, and the stack is empty. This epsilon is saying that the stack is empty. So this is the acceptability which we have already discussed and studied in the PDA's chapter, that PDA contains two different kinds of acceptability. The very first one is that the input string is completed and we reach to the final state, or if we have consumed all the input string characters or the symbols and the stack is fully empty, so we can accept this state. So that's why we call that this particular string is accepted with the given PDA transition set. So here is a practice example. You guys need to create the production transition functions for PDA, and this CFG is not a GNF. So what you guys need to do, you guys need to convert this into GNF first, and then you guys need to create the transition functions of delta for PDA. So this is the case. So don't forget to convert this thing into GNF. So that's all. Thank you.